So having seen the need for total order and unambiguous decision making in distributed system, let's now introduce Lamport's total order formulation. This is the notation we're going to use for Lamport's total order. And so what we are saying here is that if there are two events, A and B, in the distributed system, A happens to be an event, in this case, on Pi, and B happens to be an event on process Pj. If we want to assert that A totally is ordered ahead of B, that is, A precedes B in the total order, this is true only under the condition that either the timestamp associated with A is less than B, or the timestamp happens to be the same, and there is some arbitrary other function that helps us to unambiguously decide which event precedes the other. And for instance, I might say that the process ID that I associated with Pi and Pj, that may be the one that I use to break the tie. In my family car example, I told you that the seniority of the family member makes the decision in terms of how we break the tie. So for instance, in this case, if process Pi has a process ID 100 and process Pj has a process ID 200, then we could say that the arbitrary decision making in the case of a tie is that whichever process has a lower process ID, that's going to be the winner. So we might decide that in this case, if timestamp happens to be the same, then since Pi is less than Pj, I'm going to say that A precedes B. So it's an arbitrary, well-known condition for breaking a tie. So every process in the entire distributed system is going to use the same well-known arbitrary condition in order to break a tie. So that also brings up another interesting point, and that is there is no single total order. The single total order comes from the choice of the arbitrary well-known condition. I gave you this example of my family car. We broke the tie in the family car situation by saying that the seniority is the winner. Tomorrow, as a family, we could make a decision that the youngest person is going to win. In that case, my daughter will have dibs over the car over everybody else in the case of a tie. The other important point to understand is that all of this idea of associating logical timestamps with events and then deriving a total order from the logical timestamp using this kind of a method of saying we're going to just believe the timestamp associated with the respective events. We're going to believe the timestamps that are associated with the events and use those timestamps as a way of ordering them so that we can derive a total order. And if it happens to be a tie, everybody uses a well-known arbitrary condition to break the tie, and that's how we derive a total order. And once we have derived the total order, the timestamps are meaningless after that. We don't care about them anymore. The whole idea of having these logical timestamps, creating a partial order, and from the partial order deriving a total order using this formulation for total ordering is so that we can get a particular total order. And once we get the total order, timestamps are meaningless.